Thanks, Rob. So today, Neil and I are just going to give, this is a bit of an outline. We're going to talk about where we're up to with incorporating soil moisture probes and yield profit, and then Neil will talk about where the science is at and what needs to happen to bring the two together in a scientifically legitimate way. So, and then we'll have questions at the end. So over recent years, there's been significant interest in soil moisture probes, and they've been going in the ground all over the country. And farmers they have more faith in probes than they do in modelling, because they understand that it's a probe, it's a sensor, it's sending out a signal and it's detecting the moisture at a different depth layer. So what we want to do with yield profit is that we want yield profit and moisture probes to be working in perfect harmony. So the way we see it is we don't see them as competition for each other. You don't have one or the other. We see them as a nice validation, so that they can, the more information we have, the more confidence we have in both systems, so therefore we can make better decisions from that information. Okay, so where we're up to with yield profit and the incorporation is this is a representation of the system that we've got set up. So we have yield profit website where farmers and consultants get in and set up their paddocks and do all of that stuff. Feeding into that website is a database of soils coming from AppSoil, which feeds into the website. And then when the growers and consultants update the data, they save that data and that gets stored on the yield profit database. So at the moment, the way we've got it set up is that we've got probe organisations, which have, so there's any number of those organisations, and the system we've got is they're sending probe measurements and weather station data to that centralised database. So at the moment we've got it set up with one organisation, but we're in the final stages of setting it up so that it can be accessible for all organisations that are providing probes. So what happens is that a grower generates a report, request for a report on yield profit. That request comes out to AppSim. AppSim then goes and gets the information from the yield profit database and also grabs climate data from CSIRO and then runs the simulations, puts the result in a report and sends it back to the yield profit website, and one email also goes back to the grower. So that's the system of where we're at and where we're going to from here. So in the initial stages, what we're doing is that the science isn't quite there yet to be able to get the information coming to yield profit from grabbing the number coming out of the probe and feed that into the simulation. So what we're doing in the interim is we're using the probe data and the yield profit simulated data, and we're mapping them side by side. So essentially what we've got is outputs here showing the simulated soil water in a paddock compared to the probe values coming from the same site. So the solid black line here is the probe data, and the dotted black line is the simulated or virtual moisture coming out of AppSim. So the top one here is the summed graph, and then we've got each of the different depth layers where we have the individual sensors relative to each other. So the interesting point, when we look at the summed graph here, we can see that they're tracking each other quite nicely. So they're highly correlated and they're showing similar sorts of things. So water use and rainfall they're matching up with each other, which is giving us confidence that the simulation is working quite well and the data coming out of the probes is quite good as well. Look, there's obviously a glaring problem here though, is that the absolute values of both systems are about 150 mils apart. So there's something going wrong in the system here. So we've been running yield profit on this site for a number of years, so we're pretty confident that we've got it set up, got the right soil characterisation selected for yield profit here. But so what that indicates is that it's probably a problem with the calibration curves that are used in the setup of this soil moisture probe. So essentially what we need to do is to make these line up a bit more. We need to look at the calibration curves for that probe. Now the nice thing about these charts is that we're running the comparisons at all of the different depth layers. So what that's going to help us do is it's going to help us identify different layers that are where the simulation is matching up to the probes well versus layers where it's not working so well. So if we look at the example here, they're pretty much tracking each other pretty well right down at 10, 20, 30, and 40 and 50. And then when we get to the 60 centimetre layer, they're not quite as highly correlated as the other ones. So as a user, I'd look at this and say, well, let's look at the AppSim characterisation and see how that looks and whether we think it's saying the right thing, or conversely we might look at the probe and see if we can adjust the calibration curve to get them more to correspond with each other a little bit better. Okay, so another example, so another paddock from South Australia which is nearby. I'll put this one up here to say, look, in the sum graph, again we're tracking not too badly, but at individual sensors we're certainly not as highly correlated as the previous example. So this site's going to need a little bit more work, both at the individual sensor level, but to try and improve those systems so that they're performing at a level where they're similar. Okay, so to date, the majority of the interest around soil moisture probes has come from the probes themselves, but most of these probes do have a weather station attached to them. So weather stations also have a lot to contribute to improving model accuracy. So if we look at the way yield profit reports are generated or the simulations are run, there are 6 key things that go into those simulations. So we have a soil test, soil classification, which is selected to be representative of the paddock, crop details, so things like your variety, sowing date, plant density, those types of things, and fertiliser and irrigation applications. So that leaves us with climate data. So at the moment, our climate data is coming from the CSIRO patch point data set, and that feeds into the systems for the simulations, and then farmers enter their or consultants enter the individual rainfall records for that paddock. So by using the weather stations attached to the probes, we'll be able to replace some of the data from that silo database, plus the stuff that the growers are having to enter. So essentially what we're going to be able to do is we're going to be able to source current climate data from the weather station that will hopefully improve the temperature and climate data going into the model rather than getting the information from a weather station which may be 30, 40 k's away and maybe not accurately representing what's occurring in the paddock. The second part of this is that the historic data is still going to have to come from silo because these probes haven't been in the ground long enough and they haven't been recording information for long enough for us to be able to generate enough data points for those simulations. Okay, so to sort of highlight what effect these weather stations might have, we've got an example here from a research station up in Queensland. So we've got Met Station on the hill here, which is the vertical axis, and we've got the trial site, which is in the valley. So the way this was set up is that there was a weather station up on top of the hill and then one down in the valley. So even though these two stations are not very far apart, there's still a significant variation in the minimum temperatures that they're recording at both those stations. So if you're simulating a paddock at a given location and then you're getting climate data from another place, then you're going to have variation between what's occurring in the paddock and what the model's actually using to generate those crop simulations. To sort of highlight this a little bit further, we've got an example of 3 reports which were generated all on the same day from that paddock in South Australia. So the top one here is showing the yield potential for a report that was running probe data for the rainfall source. The temperature source was also coming from the probe, and the rainfall the simulated growth stage was growth stage 63. So then if we look at another report that was generated on the same day, the rainfall coming from the farmer and the temperature source from silo or the patch point data set, you can see that the simulated growth stage is growth stage 45. So that's a significant difference in growth stages between the two data sources. So, and that was obviously having a corresponding impact on the yield potential for each of these 2 reports. So a bit over 2 tonnes for the temp coming from the probe, and a bit over 4 for the one coming from silo. So why the difference? So when we went and investigated a bit further, I called the consultant who was looking after this probe, and I said, how is this temperature recorded in this weather station? He said, it's actually not a weather station. All we had was an extra port in the data logger, so we just stuck a temperature sensor there in the unit. So essentially that temperature that was coming into the system was much warmer than was what was actually occurring in the paddock. So when AppSim and Yield Profit was grabbing that temperature data, it was rapidly passing the crop through its growth stages, so it was passing through those growth stages much quicker. So the one coming from silo in this situation was probably the more accurate and more representative of the paddock. So, but what it does show is that if you have more accurate temperature on climate data going into the model, we should start to see improvements in the accuracy of the things that are coming out of it. So I'll leave it there and hand over to Neil to talk about the science.
Thanks. Yes, when people decide that they would like to use the probe data, quite often what they'll say is, how can we get the data from the probe and plug that into the model so that it uses that? Because we want to do that to improve the model's predictions. Okay? So basically what they're asking us is, how would we go about marrying models and measurements? And quite often the analogy for marriage is the old ball and chain. And it's a good analogy for what they want us to think about. What they're saying is, we've got a model that wants to run off and do whatever it would like. I'd like to have something to slow it down and make it behave. So in that analogy, the data would be the thing that they want to use to constrain and stop the model from misbehaving. Traditionally, the way we've used data to improve model predictions, though, is just been, we take the data, use that to parameterise the model, we then feed that into the model and get some output. Okay, so just a linear process, and that's been what we would do traditionally. Nowadays, there are newer approaches that help you to get much more benefit out of the information that you've got, whilst also improving your predictions. These technologies are often referred to as either data assimilation or model data fusion. So what you would do in these cases here is that you get the model and you get the data and you assimilate. You push the two together so that they can learn off of each other. So it's not just a one-way process, but both inform the other. And out of that, you get your information and improve your model predictions. So for the people wanting to use probe data with their modelling, what I'm suggesting today is this is where we need to be looking. Now, traditionally, there are three different methods that are used for model data assimilation. A very simple approach that's often used in global climate modelling and so on is the forcing method, where basically you take one of the state variables, in this case that state variable might be the soil water in the profile, and you replace that with your direct measurement. Okay, so you just take that measurement out of your probe and put it and replace the model's value with that. The problem is, when we're simulating a farm or a paddock, we're not just interested in the water content, we're interested in how you got there, and whether that water is responding to crop water use, evaporation or drainage, runoff or so on. So the journey is as important as the destination. So that first approach isn't that really useful. The calibration method, where you use the model input, and as you gather more information to improve the model predictions over time and adjust parameters, that would be a lot more useful, but it does require a large amount of computing time, okay? So that has that drawback, but that's much more appropriate for what we're after. The final method is the updating method, where if you have information over time, you update the model whenever you have an observation. So you're just using that to correct the predictions over time. But once again, even these have some problems. And so people, when they suggest putting the probe data straight into something like yield profit, they're probably either talking about that or that. But even those have problems, because nothing is perfect. The reason you're asking this question is that we know that the model has issues at times, but your probe data and your measurements also have problems. This data comes from Queensland and Norwin over 2 years, 2010 to 2012. The dots here are gravimetric soil moisture samples at different depths. Each of those is the mean of 12 replicate soil cores. And we can see in some periods there's significant variation in that. So there's some error in those measurements, there's uncertainty. The grey line comes from an EnviroScan. What we find with the EnviroScan is that quite often it's not following the same pattern as the gravimetrics. And there are periods where it has broken down and has stopped recording. Admittedly, in that point there, the site was a foot underwater, but there are issues if you're trying to model that over time. And then finally, this continuous line is the model's output there. And we've pored over that many times and we can't work out if any of those are correct. We think all of them have got problems. So nothing is perfect. And so if you have inaccuracies, what happens if you try to fix the model with that sort of data? Does it actually make things better? Well, not always. So let's look if we use that update approach. Let's say we start off with our model simulations and we're going to say, right, we're going to use the probe data to try and improve this model. We start the model, but the model starts to misbehave and over-predicts growth. As a result, it uses too much water, okay? Which isn't good, but that's okay, because we'll correct it using the probe data. So we do that, and that increases the water again back to where we think it should be. The crop then says, oh, look at all that lovely water. So therefore, growth is then over-predicted, and you've got a feedback loop. It's a bit like always recharging the credit card when a teenager spends too much. It's not going to make the situation better. You've got a feedback loop there that you can't actually stop. So, once again, I'm just wanting to reinforce. So, simple combinations of models and observations are not, they're not likely to always make things better because, one, if there's issues with the probe data, you're just going to introduce new error into the model. And if you've got a model that has its own uncertainties and you put data into it that also has error, then you get compounding or multiplicative errors when you combine them. Or, as in the last example, you can destroy compensating errors. Even if you had perfect data, if you put that into an imperfect model, you can actually make it worse because you're destroying the compensation. So, what's the answer? We've got two things with error and associated with them. We want to use them to make things better. How can we do that? Well, the thing is that this has been solved elsewhere. And a lot of this technology was developed and applied in the early days in the space program. And you're sending somebody off in a capsule hurtling into space where it's black and they can't see where they're going. They use instruments to work out where they are. Those instruments have errors. And it's important to know exactly where you are. And so what they've done is they use these techniques that can account or detect the uncertainty in the different sensors and use one sensor to help interpret the uncertainty in the other, and likewise. And so by putting those two together, you actually end up with a better result. So that's a bit like, let's do another example. Let's assume you're a truck driver who has a problem. You're always getting booked for speeding because when you think you're doing 100, you're actually doing 110. You've got a problem because you've got a very precise speedo that's telling you you're doing exactly 99. Problem is, it's precise but not accurate. But you might have a GPS system that is very, very accurate, but not necessarily precise. It can't tell you the exact speed. Well, you can use the two to solve your problem. Because if you know from your GPS that I just travelled 110 kilometres in the last hour, my average speed must have been 110. And so, as a good friend of mine used to do, he would get liquid paper and draw a little line on his speedo to say, that is actually the 100. So you're using one to infer the error in the other, and likewise. So you can use the benefits of the two to come around some of the uncertainty. You could do the same thing with the models. You've got a model that might be very, very precise, but for you might be inaccurate. You can use information from a probe that might be accurate. For example, it can detect pretty carefully or clearly that the soil might be wetting up or drying down. It may not be very precise because you've got one little probe and so on, but combine those two and you get a better outcome. Okay? So in this case here, you use the benefits of the other to improve what you're after. So, in doing that, you take things that are uncertain, multiple things that are uncertain, and gain some level of certainty, but also more information than you had before. This is what is possible. You could take your crop data, your yield data, your probe data, and your model, throw them through what is often referred to as sort of filtering techniques or whatnot, and get a range of different extra information that you couldn't detect by using them alone. By using the model and the data in combination, you can actually infer whether your sensor calibration is correct. Okay? For example, I can give you a very simple example with a simple model, a water balance model. If it rained 20 mils last night and your soil water sensors jumped by 40 mils, as in Tim's graph before, that probably means the sensor calibration is not right. Very, very simple water balance model that you can work out, and you can probably infer how you should be changing your calibration. You can detect when the sensors are not working and whether there's an individual sensor that's moving off track, just as in that last example. You can also use these model data fusion techniques to develop the model parameters. So if you are wanting to run something like yield profit and you haven't characterised your soil, these techniques could help you to infer your soil properties for your paddock, which means that ultimately you get better predictions. By throwing multiple data sources together and employing some of these fancy techniques, you get information come out that you couldn't have deduced by themselves. So the key message is, it's not, though we're asked many, many times, it's not a simple task of just plugging probe data into a model. It's more complex than that, but there's more to sort of benefit in doing it than you might have thought. Because integrating the modelling and monitoring together can provide a means to simultaneously improve both. Improve the information that you're getting from the sensors, but also improve the information you're getting from the model. Okay, including perhaps getting the calibration of your probes and the model at the same time. We've been talking about soil water probes, but it could help you with any probe or yield information. So we've been focusing on soil moisture probes, but weather station data, temperatures, rainfall, even crop yield data can help to improve the model accuracy, but also the model can help you to explain and understand your data a lot better. I hope that has helped to answer some of the questions about how one would go about integrating these things, because it's a very, very regular question that we get.